Today's lesson is the second derivative test. So we're going to take the second derivative and it is going to help us analyze our finding our points of inflection and tell us about the concavity of our original graph. So first, the definition of concavity is we're going to let f be differentiable on an open interval, and the graph of f is concave up if f prime is increasing on the interval and concave down if f prime is decreasing. So what we're going to look at here is just like a picture of this. So if this is f of x, and I know that f prime is the slope of the derivative, or the slope of the original, excuse me. So the bottom here at 1, the slope is 0. Okay, my slopes are getting what's happening with each as x increases, what is happening with the slopes. So as x goes to infinity, the slopes are increasing. They start negative and then they get really positive. So we'd say f prime is increasing, so f is concave up. All right, let's look at when the graph is, well, we can see that this is concave down. So the graph of f of x, let's look at the slopes of f. So just drawing some sketching in some tangent lines. And I can see that it starts like here. We're starting very positive. We move to a f prime of 0, f of x is equal to 0, and then the slopes get really negative. So as x goes to infinity, the slopes are decreasing. So f prime is decreasing, which means that f is concave down. All right, so what we're going to do is when we test for concavity, we're going to take the second derivative, and then we're going to find our critical numbers. We're going to look to see if f double prime of x is greater than 0. If it is, then we are concave up. If f double prime of 0 is less, f double prime of x is less than 0, then we are concave down. Our steps. It's basically like the first derivative test, except we're going to use the second derivative. And then what we find out is about our concavity, not about the original's increasing or decreasing intervals. It's about the concavity of the original. Let's start. So I have the function x to the fourth minus 4x cubed plus 2, and we're going to determine the intervals in which the original f is concave up or concave down. So we need to take the second derivative to find out about concavity. So f prime of x is equal to, power rule gives me 4x cubed minus 12x squared plus 0. And then I'm going to take the second derivative since I need that. So I get 12x squared minus 24x. We find our critical numbers. 0 is equal to 12x squared minus 24x. And then I also notice that nothing makes our function undefined. So we don't have a critical number that is from being undefined. All right, so I get 12x squared is equal to 24x. Actually, I think I'm going to do it like this. I'm just going to factor out this 12x. So I get x minus 2 is equal to 0. So x is equal to 0, and x can equal 2. Now we set up our number line. So this is the number line for f double prime. So I always label it so I don't forget because all the number lines end up looking the same. Okay. So I have a zero at, or critical number at 0 and a critical number at 2. Now we're going to test our values in between the intervals. So I'm going to use f double prime of -1 is 12 times -1 times -1 minus 2. And so I get -12 times -3, which a negative times a negative is going to give me a positive. So the values less than 0 are going to be positive. Now I'm going to use 1 because it's in between 0 and 2. So 12 times 1 times 1 minus 2. 12 times 1 gives me a positive. 1 minus 2 gives me a negative. So a positive times a negative gives me a negative. And lastly, I'll test f double prime of 3. So 12 times 3 minus 2 gives me, looks like I have a positive times a positive, which is also going to result in a positive. So from this graph, I can see that what f double prime tells me about is the concavity of f. So at when x is less than 0, the graph is going to be concave up. Then between 0 and 2, the graph is concave down. And then finally, between 2 and infinity, the graph is concave up. So intervals of concavity, we're concave up when in interval notation, negative infinity to 0 or 2 to infinity. And we are concave down between 0 and 2. Next, when do we change between being concave up and concave down? Those are called points of inflection. If the graph of f changes concavity, so changes from concave up to concave down, then what we get out, that point where we change, is called the point of inflection. Okay, so what we can do is we can find a point of inflection on the graph. So if f double prime of c is equal to 0, or we have points of inflection when f double prime of c does not exist, but we have to also test to make sure that they are actually points of inflection. So what we're going to do is we are going to apply a test. So, ooh, I didn't switch these directions. Okay, so we're going to move on and we're going to go ahead and practice. So we need to start by finding the second derivative. So I am going to do f of prime of x is equal to, and I am going to simplify this function by distributing in the 2/3. So I get x to the 5/3 minus 5x to the 2/3, giving me a derivative of 5/3 x to the 2/3 minus 10 over 3x to the negative 1/3. We do the second derivative. 2/3 times 5/3 is 10 over 9 x to the negative 1/3 minus 10/9. Actually, it's plus because the negative times the negative. Okay. X to the negative 4/3. Okay. And I can see that we're multiplying by 10/9 on both of these, so I'm just going to go ahead and take out the 10/9. I don't know, it just seems easier to me. You don't have to, but whatevs. And then I'll write this one more time as 10 over 9 times 1 over the cube root of x plus 1 over the cube root of x to the fourth. So I will have a 0 in the denominator when x is equal to 0. So I have to consider that, like x cannot equal 0. That's one of my critical numbers. And then let's get our other critical numbers by plugging in 0 for f of x, f double prime of x, sorry. So I have 0 is equal to f double prime of x. So I get 0 is equal to 10 over 9 times 1 over x. I'm going to go ahead and write these back as a rational exponent, plus 1 over x to the 4/3. And then I will divide out the 10 over 9 on both sides, which gives me a 1, and then this goes to 0. So I have 0 is equal to 1 over x to the 1/3 plus 1 over x to the 4/3. I will subtract the 1 over x to the 4/3 to the other side. So negative 1 over x to the 4/3 is equal to 1 over x to the 1/3. And then I'm going to cross multiply, giving me negative x to the 1/3 is equal to x to the 4/3. Or another way to take care of this is that if you have two fractions and what you can do is you can reciprocate the two fractions as long as you reciprocate both. So we could write negative x to the 1/3 over, or x to the 1/3 over negative 1 equals x to the 4/3 over 1. Same. All right. Lastly, I am going to divide both sides by 1/3, x to the 1/3, because then I get negative 1 is equal to, and I can use my rules of exponents. I'm going to subtract 4/3 minus 1/3, giving me x to the 3 over 3, which is x to the 1. So x is equal to negative 1. Whew, we made it through. All right, next up is to apply the number line. So I have an f double prime number line. Negative 1 is an undefined value, and 0 is another value, is our 0 or our critical number of f double prime. So we are going to test the intervals. So first I'm going to test f double prime of negative 2. And I get 10 over 9 times 1 over the cube root of negative 2 plus 1 over the cube root of negative 2 to the fourth. And so the 10 over 9 is positive. This first term is going to be a negative plus a negative. So I'm going to end up with a negative plus a negative times a positive is going to be a negative. So I'm going to do, so this is oops, I wrote my asymptote in the wrong spot. Okay, right here, the asymptote goes at 0. So I get a negative in this section. So now we're going to do f double prime of negative 1/2 is equal to 10 over 9 times 1 over negative 1/2 to the 1/3 plus 1 over negative 1/2 to the 4/3. And honestly, I'm going to type this into my calculator and I'm going to get a positive value out of this function. And then this last section, we're going to go with a positive 1. Okay. So again, type it into your calculator. I get out over. Actually, this one we don't have to type into our calculator. So a positive plus the cube root of 1 to the 4th power is also a positive. So positive plus a positive times a positive gives me a positive. Whoa. Okay. So we have concave of F, we have concave down, we are concave up, and we are concave up. So our points of inflection happen okay. So our points of inflection are at x is equal to -1. And so in order to find the y value, we need to plug in -1 into the original. I'm going to go ahead and do it down here. F of -1 is equal to 1 -1 to the 5/3 minus 5 times -1 to the 2/3. So this is going to be -1 minus -1 squared, and then the cube root of that would be 1, so times -5. So I get -6. So the point of inflection is at -1, -6. Our concavity, we are concave up when we are from -1 to 0, and then from 0 to infinity. And we are concave down from anything less than -1, so negative infinity to -1. And because there's an asymptote, we have to put the break in the graph. Right. Just to reiterate, one of the things that has to happen for a point of inflection is that you have to change in concavity. So we changed in concavity on our original graph. So at that change is where our point of inflection is going to be. If you get a number line that, say this doesn't have an asymptote here, it was just a positive and then a positive, there is no change in concavity, so that would not be considered a point of inflection. Cool? Cool. All right, let's move on to um, the second derivative test for relative extrema. So if you have a function that the second derivative is greater than 0, which means it's concave up, then f has a relative min. If f double prime of c is less than 0, then you have a relative max in that section. Right? So we're thinking like, remember, concave up or concave down, or relative min or relative max. When the second derivative is equal to 0, we have no idea what we have. So the test is inconclusive. So we have to go back and use the first derivative test for extrema. All right, so let's practice one of these. Try and make it quick. So take the second derivative. F prime of x is equal, actually take the first derivative, and I get -15 x to the 4th power plus 15 x squared. And what we need to do here is find our relative mins and the zeros so that I know where my relative mins and maxes will be. So I'm going to do 0 is equal to We need to find our critical numbers. I might have already said that, but here we go. We're going to do negative, taking a derivative, negative 15x to the fourth plus 15x squared. And I love factoring. So let's factor. We get x squared minus 1. The first factor gives us a 0 when x is equal to 0, and the second gives us a 0 when x is equal to plus or minus 1. So these are possible extrema. Now we just need to determine if they're relative minimums or relative maximums. We could use the first derivative and make a number line, but we're doing the second derivative test. So we need a second derivative. Negative 60 x to the third plus 30 x. Now, the second derivative test for extrema tells me if I substitute in a value, f double prime of, say, 0, I get negative 60x cubed plus 30 times, negative 0 cubed plus 30 times 0 is equal to 0. Okay, here the test fails. We'll come back to that one. Let's move on to f double prime of positive 1 is less than 0. So f is concave down. And has a relative max, because it's concave down, at 1 comma f of 1. I didn't calculate f of 1, sorry. Okay, f double prime of negative 1 is equal to negative 60 times negative 1 cubed plus 30 times negative 1, which means that I get a positive 60 minus 30, which is a positive value. So f double prime of negative 1 is greater than 0. So f is concave up. And when the graph is concave up, it has a relative min at negative 1 comma f of negative 1. Ba-bam. Okay, what do we do now about this test that failed? Or it's inconclusive. We don't know if we have a relative min or a max or nothing. So what we do is we have to go back to the first derivative test. So I'm going to make myself a number line. And I only need to test the value at 0 or to the left of 0 and to the right of 0, because I already know what's going on at 1 and negative 1. So I'm just going to make sure, I'm going to put negative 1 and 1. Just going to make sure I test something in between here, which let's do f prime of negative 1/2 and f prime of 1/2. And I want you guys to tell me what you get. So for negative 1/2, I got negative 15 times negative 1/2 to the fourth plus 15 times negative 1/2 to the second. We get a positive times a negative plus a positive times a positive. Ooh, which one is smaller? So this would be an 16th of 15 and a 4th of 15. So we know that the second term is more positive, so we're going to end up with a positive. So at negative 1/2, we end up with a positive. And then at 1/2, we get 15, negative, oh, wow, that's gross. Let's try this again. Okay, equals negative 15 times 1/2 to the fourth plus 15 times 1/2 squared. And we literally are going to end up with the same deal once this simplifies. So we end up with a positive. So the graph of f increases and then increases. Since both of these values are increasing, we don't change concavity or excuse me, we don't change between increasing and decreasing sections. So we do not have a relative max or min. So at x equals 0, we have neither a relative min or max at x is equal to 0. Wow, that was a lot. Okay, so that's it.